Hey everyone. Today we're going to be learning about the derivatives of exponential functions. So today is a little investigative in nature. I'll be asking you to do some numerical investigations, getting you set up for those, and then kind of bringing you back and having the answers filled in and having a little chat about what you guys found out. So let's dive right in. So our goal for this first investigation is to look at the derivative of the function f of x equals 2 to the power of x. So the base is 2 in this case. We're going to do that by finding the slope of secants that are really, really, really close together. So you can see in the left-hand column here, I've got 7 different points that are all on the function 2 to the power of x. And I've got nearby points. So there are 1/100th away from those points. And I've got the y value, kept a lot of accuracy. And so when we find the slope between those 2 points, the slope of that secant, it should be pretty close to the instantaneous rate of change, the slope of the tangent line, or the value of the derivative. So I'm just going to do one of these with you, just to give you an idea of what is expected here. So let's do the first one. So to find the instantaneous rate of change, or like a very close approximation to it, we're going to find the slope of the secant. So that would be, we find the difference in the y's. So 0.12587 minus 0.125. And we find the difference in the x values. So a negative 2.99 minus negative 3. I'm not going to do all these in this video. You don't have to worry about that. That would actually take a really long time. I've got the solutions done ahead of time, but just going to do this one on the fly with you guys here. And that would be divided by 0.01. So we get 0.087. So that would be the value of the derivative. At x equals negative 3, 2 to the power of x, the slope of the tangent line is about 0.087. And you're going to do that for all 6 other points. One other thing I'm going to have you guys calculate is the ratio between the derivative value and the function value. So I'm going to have you guys do that ratio. So if you do 0.087 divided by 0.125, I want you guys to do this too. And in this final column, I got 0.696. So those are the 2 things you'll be doing for all 6 points. Calculate the instantaneous rate of change, or a very close approximation, by finding the slope of the secant between these 2 points that are very close together. And then we're investigating the ratio of the derivative value and the y value of the original point. So I'm going to leave the final 6 to you guys. If you want to pause the video, do those 6, and come back when you're ready. Okay, here are the results that you should have got. So you can see I've got my first one done already there. I'll have this fixed up on your lesson sheet, but yeah, I just had a couple sign errors there. Didn't mention that in the previous slide. But yeah, these are definitely positive y values. But yeah, that's fixed up on your lesson sheet. So we can see we got the rates of change, and we can see they're kind of increasing at a faster and faster rate. And what's cool is these ratios of the derivative to the y value actually stayed pretty close. They're all around 0.696, which is pretty interesting. We're going to talk about the significance of that later. But this is saying the derivative divided by the function kind of gives you a constant value. Doesn't matter what the x value is. What I also would like to have you do in this investigation. So I've got a graph of 2 to the power of x here. You calculated the derivative for 7 x values, -3, -2, -1, 0, 1, 2, and 3. And I want you to plot the values of the derivative on this graph too, over top of the graph of 2 to the power of x. And we'll see what that looks like too. So if you want to pause the video, plot those 7 values for the derivative, and then kind of see what you notice. I'm going to flip to the solutions here. So if you plot those 7 values for the derivative, so you've got the original function. This kind of went off my screen grab a bit there. The original function is 2 to the power of x. And we've graphed the derivative. So remember, right now, we don't really know, like we don't have an equation for the derivative. But what we can kind of see right now is, the original function was an exponential function, 2 to the power of x. It looks like the derivative is an exponential function too. It looks that way. Also, for the, it looks like here that if you look at the graph, it's increasing it's below the original graph. So it's increasing at a lower rate, which means the base is less than 2. So for this derivative, the base of our exponential, the derivative is exponential, and that exponential function is going to have a base less than 2 because it's not growing as fast as the original. So pretty interesting. We're going to do this, repeat this process one more time, but for 3 to the power of x. So I've got another table for you guys. I have 7 points on 3 to the power of x. And this time I'm just having you guys calculate the y values as well. So you plug -2.99 into 3 to the power of x, get a decimal value. You can keep lots of accuracy, find the rates of change, just like you did in the previous one, and find those ratios as well. So you have 7 to do. Even if you're doing this with other people via Zoom or Discord or what have you, maybe split up the work. Or if you just want to you can do a few and then just like copy down the rest for me, let me do half the work, that's fine too. But yeah, you can pause the video, try that. And here are the results. So you can see I kept a lot of accuracy for my y values. I did the slope between those 2 points to get an approximation for the derivative, instantaneous rate of change. And you can see that these guys are increasing too, and they're increasing at a faster and faster rate. And this ratio, it's a different number, but it's constant again. For the most part, they're all very close to 1.105. So that's really cool too. We saw kind of similar things happening. And then if you guys would also plot those derivative values over top of this function, I've graphed 3 to the power of x on this sketch here. Overlay your derivative values, and yeah, pause the video, give that a try, and here's what the results are. So the derivative values are just a little bit larger than the values of the function, but this similar things happen with this one. So what do we notice here? The derivative of 3 to the power of x, we don't know exactly what its equation is, but it is exponential. We can see that. But this time, the derivative values are higher than the curve. So whatever this derivative is, the base of that derivative will be more than 3. Which is really interesting too, because that means as you go from like 2 to the power of x to 3 to the power of x, there'll be some base value in the middle there where the function and the graph of the derivative will be right on top of each other, and they'll be the same function, where the derivative of the function is just the function itself, which is really very interesting. So that's kind of where we're going. We have some things to talk about. So let's summarize with some key ideas here. Okay, so the first one, hopefully you guys are convinced. We made those two, we made 2 graphs. We found some values for the derivative, we plotted them. I hope that you're convinced is that the derivative of an exponential function, it's also an exponential function. Our second key point here, hopefully you're convinced of this too, is when you guys said the ratio of derivative to the y values, you get a constant, which means that the derivative is a constant times the original function. So if the original function is b to the power of x for some base b, the derivative of b to the power of x is some constant k times b to the power of x. That's what we've shown since that ratio is constant. And that value of k is different for different values of b. We saw if I flip back for 2 to the power of x, the value of k is about 0.696. For 3 to the power of x, it was about 1.105. Later on, we'll actually understand what that value k is. But right now, we just know it's some constant k, and that value of k, it changes for whatever the base is. And that's what we have in this last point here. The value of this constant k depends on the value of the base b. And what we saw is for some base b between 2 and 3, the graphs are going to cross each other of the function and derivative, and they'll be the same graph. The value of k will be 1. They'll be the exact same. And the derivative of b to the power of x will be b to the power of x. And the second derivative will be b to the power of x. And the third, which is really cool. And so we're going to, over the next with the next little mini investigation and our next lesson, investigate some things about that number. It's a special number. It occurs quite a lot. It's called Euler's number. So that's the big learning for today. Derivative of an exponential function is exponential. The derivative is a constant times the original function. And that constant depends on the value of the base, but for somewhere between 2 and 3, that value is going to be 1, and the derivative of a function will be, of an exponential function, will be itself. So that's really cool. All right, so this little mini investigation right now appears disconnected. It's very unrelated to, except for the fact maybe this expression has an exponent in it. It is not related to the 2 investigations you've done. The special number between 2 and 3 that derivative property holds is called the natural number. It's called Euler's number, and it's we use the variable, the letter e, to represent that. Like we use pi is 3.14159, blah blah blah. This value e represents that special number between 2 and 3. So what we're going to show here is that number actually occurs in this cool numerical sequence here. Evaluating this expression, 1 plus 1 over n to the power of n. So let me do a couple with you, and then we'll have a little team talk afterwards once you guys have completed some. So for this first one, if you plug in n equals 1, you get 1 plus 1 over 1 to the power of 1. So that's 2 to the power of 1, and that gives us 2. I'll do the second one as well. Shouldn't be too bad to do with mental math. We have 1 plus 1 over 2, and we'll use that to the power of 2. So that's 1.5 squared, which is 2.25. So I want you guys to do n equals 3, 4, 10, 100. And then maybe if you want to even try some higher values, I might even just throw this in there. I did some higher values in my solutions. So try n equals 1,000, maybe 5,000, maybe 10,000. I'm not sure if these are the exact. I might have used like 500 if you want to do like f.5 or something. But yeah, just try some higher numbers too, and see if those values are, the results ceases to keep changing. See if it gets to a fixed number. So let's have a little fun, do these calculations, and let's see what we get. And if you're ready to go, you can unpause. You can pause the video, and then when you're ready, unpause. And here's what I got. So 2.25, 2.37, when n is equal to 100, got 2.705. Yeah, and I did 1,000, 5,000, 10,000. And actually what's cool is when you get to 5,000, 10,000, to at least 3 decimals anyway, the result doesn't change. And you get this number about 2.718 to 3 decimal places anyway. This is that special number between 2 and 3 that gives us the derivative of an exponential function is itself. The why that is, right now it appears, right now you guys aren't sure why. But that is the number, and it's the natural number, it's Euler's number. And it's the special result of the limit of this sequence. As you let n approach infinity, make n really, really, really big, this sequence of numbers approaches Euler's number, about 2.718. The significance of this, which we'll talk more in our next lesson, is that if f at x is equal to e to the power of x, and remember e is just a number, it's about 2.718, then the derivative of e to the power of x is just itself, e to the power of x. Pretty cool, pretty powerful stuff. So in our next lesson, we are going to talk more about the natural number and maybe start investigating where it comes, like how it comes into our work with derivatives. So for next steps, you guys are just going to kind of play around with some investigations and the natural number. I have posted a PDF of practice from the McGraw-Hill text, section 5.1. Give these guys a try. As usual, if you need help with anything, please let me know. I'd love to help you out. That's it for today. Hope you have a great day, and we'll see you guys soon.